Okay, hi everybody. So today we're going to continue on 5.1 and hopefully we get to finish it in this video. But in the first video, we really focused on what was called sigma notation. And the reason that we focus on sigma notation is because when we do the area problem for finding the area under a curve, we're going to want to eventually, towards the end of the video, make our rectangles as small as possible in order to get the best approximation for that area. So what am I talking about exactly? So let's say that you are given a random function. You don't really know what it is. Okay, and let me just draw this random function. Make this, and it looks like this. Oh, wow, not like that. Like this. Okay, and then I asked you, okay, let's say this function is y equals f of x, and I'm telling you, okay, between a and b, I want you to find the area under this curve. So how do we find the area? Well, if I want to find the area, maybe it's a good idea to let's draw some bounds. And now our job is to find the area under the curve, which I'm going to call S here. So we're going to try to find the area of this surface right here. Oops. Okay, but here's the thing. How do we find the area of something that looks like this? Well, the thing is, we don't have a formula for this. The areas we do know, for example, are areas like length times width, and that's for a rectangle or a square or whatever. Or we know the formula for a triangle. That formula is area equals base times height for a triangle. And we also know the area of a circle. And we know a few more, but these are the most common ones. So A is equal to pi r squared for a circle with radius r. So these are the ones that we usually tend to not forget for areas. But how is this going to help us find the area of something like this? We don't know how to find it. I mean, what can we do? There's nothing that we can do. We don't have a set formula for this, but good news is that calculus can actually help us find it. But before we get into how to get the best approximation, let's kind of go back to how can we break up this problem in order to, maybe we can't exactly get an accurate answer just yet. We will eventually. We'll work into that in the later sections. But for now, how did they approximate it? Because, math has been around for a while, and I want to know how they did this. And so what they did is they used the areas that they knew to their advantage in order to approximate an area like this. So let's do a quick example, and then we'll finalize these formulas in just a second. So for an example, let's say we had the function y equals, or f of x equals x squared, and I want you to find the area between 0 and 1, okay? I want to look at the interval 0 and 1, and I want you to find the area under it. So I'm just going to draw that small interval, and I'm going to draw the function y equals x squared from 0 to 1. And so that's just the left-hand side of the right-hand side of a upward parabola, a concave up parabola that looks like this. And let's call this point 1, 1. So we're looking into finding the area between 0 and then 1. Okay. So here's the thing. We know we want to find the area between this, but how do we do it? This shape is nothing like we've ever seen before. I mean, it looks like it kind of wants to be a triangle, but it's not. What we did, or what we're going to do, is we're going to break this shape up into intervals. And let's say we break it up into 4 intervals. So we're going to break it up into 4 intervals between 0 and 1. So if we break it up evenly between 4 intervals, this is why I chose this one, so that we can easily see it. If we break it up in half, I'll get a 1/2, and then break it up 2 more times. Here I'll get 1/4, and here I'll get 3/4. And so what we're going to do now is we're going to use these formulas here, and we're going to really use the area of a rectangle here in order to approximate this. And I just want to point out that we are really zoomed into this function right now. So the error for this is very small. But another thing to note is that this area here has to be less than 1 for sure, because we're doing an interval between 0 and 1, and then if we pretended to draw a rectangle here, right? The area of this big rectangle here is 1. So obviously this part here has to be way less than 1. Okay, so at least we know that, so that when we approximate something or whatever we approximate, we need to make sure that it's less than 1, because it can't be greater than 1. Okay, so what we're going to do now is we're going to approximate this using the formula of a rectangle. And so what I'm going to do now is I'm going to go to my 1/4 spot, draw a line up to my function, and then go to my y-axis. So I can get a perfect rectangle. Same thing here, but here I'm going to stop at the 1/4 mark and go here. Here I'm going to go to my 3/4 mark, stop at where the function hits the graph, and go here. My rectangles are kind of ugly, but they're supposed to be straight. Here, and then this way. So here we can agree, and hopefully we agree, that the width of each one of these rectangles is 1/4, because I cut my interval into 1/4 pieces. I said I'm going to cut it into 4 pieces, and it's between 0 and 1. So each of these little widths right here is 1/4. Okay. And so now, in order to approximate this area, right, if we use these rectangles in order to approximate it, well, the area that's drawn in red is going to be the area of this rectangle, this rectangle, this rectangle, and this rectangle, all added together, all summed up together. Hence, this is why we started going over that sigma notation, because it's going to come in handy later on in this section. And so if we approximate this area, right, my width here is 1/4. So the area of this one, and let me draw it in like a different color. Let's do pink. Let's just take a look at this one for now. I'll erase this in just a second. But the area of this one here is going to be 1/4 for my width. And then my height, or my length times width, so my width is 1/4, and my length here is how high this is. And how high this is depends on how high we are at this point here on the function. So this is actually going to depend on the function itself, because we want to know what's the y value at this exact same spot. So in order to find that, if x is equal to 1/4, my length is going to be 1/4 squared. Okay, so it's going to be 1/16. So here for this rectangle, and let me just draw it over here. I'm only going to do this for one of them just so you guys can see where I'm going. For this one here, my length is going to be 1/4 always. But now my height here, my width is 1/4, and my height is going to be 1/4 squared, because that's the point here. That's how long it is, and that depends on where we're at in that function. And now we're going to do that for all of them. So we can agree that for that first rectangle, it's going to be 1/4 times, so we're doing basically width times length, right? We're just cutting that in, cutting up this function, and then this is going to be 1/4 all squared. And now if we do the next one, this length here is still 1/4, But now my height is going to depend on this spot for that function. So it's going to be 1/2 all squared. So it's going to be 1/4 times 1/2 all squared plus, I'm going to do the same thing for the next triangle here, is going to be 1/4 times 3/4 all squared. And then the next one is going to be 1/4 again. And now my height here is just 1, so that's nice. So my height here is just 1, and then it's going to be 1 all squared.
Hello, people.
So we approximated this area, and if we sum them all up, we'll get approximately 0.46875. I did this ahead of time to save some time for this video. So if you add them all up, put it in your calculator, that's what you'll get. But here's the thing, is we approximated this one way. Look at where we drew our triangles. We started our triangles over here. At 1/4, went up to the function, and then drew a straight line. But that's not the only way we can approximate this area. We can also approximate this area by using a different type of rectangle or a different approach to drawing those rectangles. So let me get a different color. We could have also gone here, and then from here, gone up to the function and drawn this rectangle this way. From this part here, go up to this function and go this way and draw the rectangle this way. And then we can draw the next rectangle from here to here. And now we get different rectangles, but we're still approximating that function. As note, for the red one, we kind of have some error here. We have an overestimation. It's not going to approximate the graph exactly. And for the green part, looks like we have an underestimation here. But it's still an estimation, right? So we can still use it. And so if we wanted to approximate the green part, we can say that the green rectangles are going to be equal. Our width is still the same. Our width hasn't changed. Our width for all of these is still going to be 1/4. But for my first rectangle here, my height is 0. Because what I did is I started from the end, or from my left-hand side, so my left endpoint here, 0, and then I drew that rectangle this way. So I basically, here is where it touches the function, and I went this way, and then when I get to my next point, I go up this way, up this way, up this way. And here my point is 0, so this is going to be 0 squared, which makes sense because there's no function there. And then my next one is going to be 1/4 times, let's look at the function, it's going to be 1/4 squared plus 1/4 times 1/2 squared for the next rectangle, and then plus 1/4 times 3/4 squared. And then notice I don't actually get to hit that one spot. And so when we approximate this, we get roughly about 0.21875. And so it's okay if you don't really know what's going on here. Here I'm just kind of introducing what we're going to be doing in this section. It'll become more clear once I establish these formulas for sure. Later in this section. So now we know that the area of our rectangle is going to live between 0.46875 and between 0.21875, which is pretty close. Now we know somewhere roughly around where this area lives. I mean, this is obviously an overestimation, and this is an underestimation. So our area lives between those two numbers. And so that's the idea that we're going to be doing in this section. And for this section, we're actually going to be calling this red spot, since we started on our right-hand side here, we're going to call this our right endpoint. And since we cut it into 4 intervals, our subscript is going to be 4. And for the green one, since we started on the left-hand side of the function, we're going to call it L with our 4 cuts of our interval. Okay. And so in the next page, we'll establish how we're going to go about approximating areas under the curves. But this is just like a good example so that you can see where we're going to go in this section. Okay, so what we want to do now is, in the last example, I gave you an idea of how we can figure out the area under the curve over an interval. And the idea was that we break the function up into intervals, smaller intervals, and then we make a rectangle out of them, and we can either use the right endpoints or the left endpoints to approximate the area. So what we mean by that is we can start at x equals 0, or we can start at x equals 1/4, which we're going to call this the 0th position and the 1st position. So how can we go about approximating the area under a curve given any function? So recall that the goal is to fill the region with rectangles in order to approximate the area. So our goal here is we're using rectangles to approximate the area. And right now it's just an approximation because, as we've seen in the other example, we can have overestimation or underestimation. So here we are going to fill the region with rectangles to get an approximate area. And so again, this is an approximation of an area, not exact. But here the thing is, the more rectangles, the better. Because the more rectangles that we have, the smaller the rectangle is, and the less we lose, or the less we overestimate. So having more rectangles is actually good. For your homework in this section, it'll probably specify how many rectangles you need. So you don't need to worry about it in this section, but what you do need to worry about is the more rectangles that you have, the more of an accurate estimate you'll have. So after that, we're gonna say that, let's say we have n rectangles. So for n rectangles, we're going to what's called a partition, which just means that we're breaking up the interval. So you're taking parts of an interval. Into n subintervals. Let me move that over. I thought I was gonna have more room. Oh, that's disgusting. And so what that means is, like, for example, in the last example, we had an interval we were looking at. We were looking at the interval 0 to 1. And then what we did is we partitioned this into 1/4. And so now we get many subintervals here. Each one of these is a subinterval. So we'll get n subintervals. So if we have our endpoint A is going to equal x0, which is our very first endpoint, which x0 is less than x1 is less than x2, and then we'll go all the way to xn, which is going to equal our last endpoint. So this is what we mean by this, and this for example, for this one, it was here, this is our x naught, this is x0, all the way to our last space x of n, which is b. And we have n of them. And now what we're going to do is, in order to find the width of the rectangle, so let's say that I tell you, hey, I want you to partition your rectangles into 4. What you would do is you would take your left endpoint, your right endpoint, and then subtract your left endpoint and divide by n. For this example, we knew we wanted 4 intervals, so what we did is we cut it into 4 pieces, which led to each rectangle being 1/4 in size. And this one was easy because our width, our interval was between 0 to 1. So it's easy to tell what our width is going to be each time. But what if I told you, oh, we're looking at the interval from 3 to 10, or 3 to 7, or 4 to 5? Then we wouldn't be able to just kind of do it. This one was an easy case. What we would do instead is the width of our rectangles will always be so our width of rectangles, we're going to call delta x, so a small change in x. And we're calling it a small change because the idea in the long run of this problem, or this area problem, is that we want to make delta x as small as possible so we can get the best approximation ever. So delta x is going to be equal to b minus a all over n. So that just means that if you have some random function here, you don't have to draw this. And let's say you don't start at 0. Let's say a starts here and then b starts here. And you want to cut it into, like, let's say 7 intervals. In order to get the width, what you'll do is you'll subtract b minus a and divide by 7 in order to get an even width for all of them. And the points are given by and we're going to call them xi, is equal to a plus I times delta x. So what does this exactly mean? This one specifically is for our right endpoints, when we're doing right endpoints. So we'll start our endpoints off at 1. And then what we'll do is we'll start at our first spot, A, and then we'll multiply it times I times that delta times the ith place here. And I'll show you what that means in a second. And so now what we're going to want to do is we're going to actually, I'm going to write it also down for our left endpoint. And for our left endpoint, it's going to be equal to, still we'll start off at our right. So at first we'll start off at A, and then we're going to add delta x times I minus 1 for our left endpoints. Because here we're starting at the very end. So for example, here, for this one, this is our left endpoint. And then this is our right, where we, and for our right one, we started here, moved up to the graph, and went this way. Okay, so that's the idea here. And so we can generalize this and say that our right endpoints can be written as R of n. And so remember that n is the size of your endpoints. And we'll get n is the size of your, n is the size of how many rectangles you want. So our right endpoints are going to equal f of x1 times delta x plus f of x2 times delta x. plus f, and well, so I say from, I don't want to write to it, plus dot 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 f of xn delta x. Okay, and then for our left endpoints, there'll be L of n, so L for left, and for the number of intervals we're going to have. And now it's going to start off at f of 0 times delta x plus f of x1 times delta x plus dot 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 f of xn minus 1 times delta x. So on your homework or on an exam, I'll specify either for you to find the left or the right endpoints. And here I'm writing dot dot dot. And in 1 second, we'll actually learn how to write them using that sigma notation we learned in the last video. But the idea here is that you're just going to be adding each area. And it's nothing actually too crazy, because if you think about it, we're cutting it into intervals and we're approximating that area, right? All of these is a width, right? This is our width times our length. So how high we are in that graph. So it's actually things that you've learned before, but now we're applying them to calculus problems, and we're expanding our knowledge a little bit more on, hey, how can we use such a basic example to get a really good approximation of an area under the curve or of something I don't know the area of, and this is how we will do it. Okay, so now that we talked about how we define right endpoints and left endpoints, we can define what is an area for our region S. So the definition of an area using these methods is that the area A of a graph that lies under the graph of the continuous function f, so some random function, is the limit of the sum of the areas of the approximating rectangles. So what this is really trying to tell us is that when we sum up all the rectangles together, we should get the area of A. But we already seen that when we cut the function in rectangles, we run into this problem where we begin to overestimate or underestimate the rectangles and the areas. So we run into this error. So what we can do to avoid that is that if we take our triangles, right, and we have a function that we're trying to approximate, if we make the rectangle so tiny, right, we'll actually get the full area of the graph. Obviously, I'm being a little bit dramatic here, but if we have that function, if we make the rectangle so small, then we actually won't have any error. And so that's what we're going to try to do when we're approximating these areas, is we're going to make the rectangle so small. So that means that if we're trying to make the rectangle small, that means we have to have a lot of n values. We have to have a lot of rectangles. And so in order to get a lot of rectangles, what we're going to do is we're going to take the limit to infinity. Now this formula has it with the right-hand sided limits, but it doesn't really matter. If you use the right hand or the left endpoints of your approximation, if you're taking the ends to infinity, you'll get the actual area of that surface, because it doesn't matter which ones you're doing if they're infinitely small, right? If they're infinitely small, you'll for sure approximate the area as a whole. So just keep that in mind. It doesn't matter which one if we're both taking the left and the right hand sided to infinity, but we need to take that limit. And there's a proof to this, but I'm not really going to go over it. If you would like to go over it over office hours, that's fine with me. But this section is already kind of long, so don't want to add any more to your plate. And so let's do one more definition. And this is also true that if you use the left-hand sided limit too. With obviously, we would use the x naught over here, but just wanted to write one down. So either one you use is fine for approximating, and then we'll do a couple examples in the next video, because this video is already going to be long as well. And so the next thing we're going to do is we're going to define sample points. We're going to define our sample points because we've defined left endpoints and right endpoints, but we haven't yet defined it for random sample points. And so the definition of a sample point is that basically, if we wanted to generalize this so that we didn't have to use a left or a right-hand sided limit, we can generalize this using sample points. So in general, for any points, xi, and we'll call them xi star, in the interval, in any interval given, for finding the height of a rectangle, these are called sample points. And so the area of the region can be given by this. So before we specified it using a left or right-hand side limit, and now we did it in general. And this is what's going to be called a Riemann sum, which we'll actually go over in 5.2. And because I'm covering a lot of this stuff in 5.1 already, 5.2 should be a little bit shorter because I'm already going over a lot of these concepts because it just really makes sense to tie them all together. So if you do it for any amount of points, as long as you're taking them to infinity, you can do it, and this would be the general, okay? And so now that we have that, now writing this is kind of a pain. And at the first video, we went over how to actually, how to write it in sigma notation. So now let's actually write these formulas in sigma notation so that you have them. And so then you can use them whichever way you want or whatever way is easier for you to remember. But using them in sigma notation, as we've seen in the first video, can help you when you're trying to evaluate them, because if you're taking n to infinity, you're not going to just add a bunch of points up over and over again, right? That's crazy. So area with sigma notation. And in order to evaluate these values with sigma notation, it's really helpful if in that first video, if you were really paying attention, is those formulas that I gave you for the sum for I, the sum for I squared, the sum for I cube are really going to come in handy when you're evaluating these, especially when you're taking that limit to infinity. So keep that in mind. So let's let n be any integer, then our left endpoints are equal to the limit as n approaches infinity from the left-hand side, which is equal to the limit as n approaches infinity for the sum of n I equals 1 of f of xi minus 1 times delta x. So this is just for the area going off to infinity. So, which makes sense. Here we're starting off with 0. So if we go back up here, right, we're adding them all up. And here this is just, it looks really fancy and it looks super crazy, but it's really just length times width here. And you're just adding them all up over and over and over again, and you're adding the left-hand side limits. So now that we have that, we can also define the right-hand side limits. And then for the right-hand sided limits, we'll basically get the same thing. It's going to be the limit as n approaches infinity of r sub n, since we're dealing with the right-hand sided limits. And then we're going to do the sum from I equals 1 to n of f of, and now f of xi, not f of xi minus 1, times delta x. And now for any sample points, so it doesn't matter which one you use, we'll have that the area is equal to the limit as n approaches infinity. The sum is I equals 1 to, from I equals 1 to n of f of xi star, so our sample points times our width. And so all I did here is I took what we notated here, and since we're just adding the same thing over and over again and iterating through those values of I, we can write them in that fancy sigma notation. Okay? And so these are going to be your superstars in 5.1 and 5.2. So keep these in handy because these are how you're going to be evaluating them. And then we'll go over exactly how to do them with a couple examples in the next video. But before I move on to the next video, I do want to make a note about what happens with the left endpoints and the right endpoints. Because as we noticed over here, when we computed the right endpoints for this function here, the right-hand sided endpoints ended up overestimating. And the left-hand sided limits ended up underestimating. But that's not always the case. Sometimes the right-hand sided limits actually underestimate and the left-hand sided limits overestimate. It just depends on what's going on with your function. So what we want to do is, I'm going to say, I'll write this down formally in just a second, but if your function is increasing just like this one, our function is strictly increasing for this small interval from 0 to 1, right-hand sided limits will tend to overestimate. Actually, not tend to, they will always overestimate the area when you're doing it for a smaller n. They will overestimate the area. And if you have your left-hand sided limits for an increasing function, you will underestimate. And it's actually going to be the opposite when your function is decreasing. When your function is decreasing, your left endpoints will overestimate and your right-hand sided limits will underestimate. So let's actually write that down formally. So let's make a note here. And this is a really good concept for me to put on the exam. Knowing when things over and underestimate, this tells me you're really paying attention. Okay, so let's write down, I just wrote down what I just said. So if the function is decreasing, then the left points will overestimate. And we did an example like, we didn't do an example like this. And so the reason is that if we look at this example here, is if we have a function that's strictly, so if we go ahead and take a look at our function here, we are decreasing. And if we check the left endpoints of our function, then what we're going to do is we are going to go up from the function. And then as soon as we hit the graph, sorry, that was horrible. We're going to go down and draw that rectangle. Similarly, we'll go up here, draw that function, and we notice a little bit of overestimation. Now, this graph isn't the most accurate just because of how small I drew it, but it's just to give you an idea of what's going on with this function. We'll draw a line here, diagonal, and here you can see the overestimation a little bit better. And this is just doing my left endpoints. As soon as I hit my function for this xi, I'll come down. There's that overestimation and that overestimation. But if I go ahead and check the right endpoints here, right, my right endpoints will start here. I'll come to my function, and then I'll hit this way. Like, you can't really see the overestimation there, but underestimation there, but because it's so close right there. And then if we do the same thing on the next part, we'll hit our function here for our right endpoints. And then here we'll hit our right endpoint here. And then go this way. And now you start to see that underestimation just a little bit. And that's just an example of, if it's decreasing, it's an underestimation. And if it's increasing, it's overestimation. So if it's a decreasing function, the left endpoints will overestimate. And if we calculate the right endpoints, they'll underestimate. Vice versa for this part here is if the function is increasing. So what I mean by increasing is that if we have something like this, like the first example we did, then the right endpoints in this case will overestimate and the left endpoints will underestimate, just like the example we did over here. So here's an increasing function, and our right endpoints here overestimated the function, as we see here, and our left endpoints underestimated the function here. I just drew the graph a little bit nicer than I did over here. Okay, but if we take our n values to be smaller and smaller and smaller, or if we take our n values to be larger and larger and larger. So the more rectangles we have, the better approximation we get. So the more rectangles we have, the lower and the upper sum actually approach each other. So this is all this last statement is saying here, that as the number of rectangles increase, the lower and the upper sums will approach each other. And that's because if we have a function like this, it doesn't even matter what it is. Let me just pretend that's that. And we were looking at the area between a small interval. If we look at trying to draw really infinitely small rectangles, let's say a 0.10 rectangle or a 0.00000.1 rectangle in width, then eventually we'll have enough to be able to fill this in with no over or underestimation, and it won't matter whether you're taking the left or the right endpoints, they'll approach each other. But that's just a visualization. Don't draw that, that's kind of ugly. But that's just so that you can see where it's going. Okay, and so in the next video, we'll do a few examples, and that one will be pretty short. So